Good morning, everybody. Hope you're having a great day. Hope you had a mildly nice weekend. Good morning, Michael. Good morning, Ryan Schwartzmeyer. It's sunny today, which is good. Last week was so dreary. Which, I mean, dreary weeks are honestly better for doing homework. But they're so dreary. I had a lot of questions about the programming project this weekend, which is awesome. I mentioned this morning, how do we do part 3A, P3A? You know, Ryan, honestly, it doesn't matter. Your script files, it matters what they're called. Your homework, PDFs, it really doesn't matter because it's all associated with your name on UB Learns, so I don't care. Homework 11, P3A. Okay, so if you think about Kramer's rule, Kramer's method, whatever you want to call it, Kramer and his solution, what is the solution? I mean, you're going to take the determinant of A1 over the determinant of A. What kind of values do you need in order for that to work out? Like if you think about trying to divide by the determinant of A, what is an invalid number to divide by? In reality, Kramer's method can be used for any system of equations where A is invertible. Yeah, so it just can't be 0. So any value of P, such that your determinant isn't equal to 0, is fine. So we are learning a lot of different methods for solving. I mean, yeah, Michael, you pick a number and then you have to show that it works. But yeah, that's really it. I mean, you can figure out what P can't be and then pick something that's not that. But in reality, just pick a number and show why it works, explain why it works. So we're learning all of these different methods for solving systems of equations. And in reality, there's 3 different sets of equations, and we'll talk about this next week. But three different types of equations that we can have. We can have a system that has one solution, we can have a system that has no solution, and we can have a system that has an infinite number of solutions. And like I said, we'll learn this next week. But the determinant tells us more or less which one of those options we might have. So as long as your determinant isn't 0, that means that your A matrix is invertible, which means you're going to end up with one solution, one unique solution. If your determinant is equal to 0, then you might have one of the other two. You might have no solution, or you might have an infinite number of solutions. So our determinant can tell us more or less what type of system we are going to have. So if our determinant is 0, we have one unique solution, and it's great. It's fine, dandy, we are good to go. And different methods can be used in different situations. Gauss-Jordan and Gauss elimination can more or less be used in all of our scenarios. Gauss-Jordan and Gauss elimination can be used to if we have one solution, if we have an infinite number of solutions, or if we have no solution. It'll tell us if we have no solution, and we'll learn how next week. Some methods can only be used if we have one solution. So if we want to multiply B by the inverse of A, that means that we need to have one unique solution, which means our determinant can't be 0. If you want to use Kramer's method, we need to have one unique solution, which means A needs to be invertible, which means our determinant can't be 0. For row echelon, so REF, can there be a 0 on the upper right corner, or is it strictly in the bottom? So, Flora, that's a good question. For row echelon form, the zeros, the triangle of zeros is in the lower left corner. You can end up with zeros up in the upper right, but those would just magically appear. No, I shouldn't say magically, but those would just appear as you're doing your operations. We really, for row echelon form, it is by definition the lower left triangle is zeros. Let's see, what other methods do we have? Today's method, we're going to talk about LU factorization. At the end of the day, LU factorization is similar to Gauss elimination, but we really, we can't, I guess we could do it for any scenario. It could work for any one of those scenarios. But yeah, so different methods have different pros, different cons, and we can choose the one that fits our situation. I think for the final exam, I'll pick one system of equations and solve it with all our different methods to show how they compare. But once again, different systems are going to be harder to solve in one version versus another version, depending on what operations we have to do. How difficult is it to find a determinant? How difficult is it going to be to do these row operations, etc.? Okay, good question. Let's start. It's time for us to start. Let's start. So for this set of material, we are going through what's called LU factorization. LU factorization. When we're talking about factorization, we're literally talking about breaking up our matrix into a product of two matrices. So if you think about factorizing 6, the factors of 6 are 1, 2, 3, and 6. In order to get 6, I can say 1 times 6 or 2 times 3. That is a factorization of 6. Same idea for LU factorization. We're taking A and we're figuring out can we break it up into two different matrices, a lower triangle matrix and an upper triangle matrix. So that's what we're talking about when we say factorization. We're just finding two matrices such that A equals the product of a lower triangle matrix times an upper triangle matrix. And in order to find an LU factorization, we are going to only use row operation 3. So if you remember last week, I emphasized the fact that row operation 3 looks like this, where row something is replaced by that row plus some multiple of another row, where this here is a 1, where we cannot multiply the row we are replacing by a number. So we are going to apply row operation 3 in order to find LU factorization, and only row operation 3, which means for a 3 by 3 matrix, we are always going to use these 3 row operations. The first one is going to be row 2 equals row 2 plus some multiple of row 1. It's always the first one. The second one is going to be row 3 equals row 3 plus some multiple of row 1. And then our third one is always going to be row 3 equals row 3 plus some multiple of row 2. We are always using these 3 row operations in order to do LU factorization. Every single time for a 3 by 3. For a 4 by 4, we would have more, but for a 3 by 3, these are the ones we use. Okay. In your homework, you'll have to do a 4 by 4. I will go over that at the end. For your exam, you will only have to deal with a 3 by 3. Okay, so my goal using LU factorization is to take an A matrix, it's always going to be a square matrix, and break it up into a lower triangle matrix times an upper triangle matrix. And I'm always going to do that using these 3 row operations. So let's do that. So for this matrix, I'm going to first do row 2 equals row 2 plus, I need to get a 0 here. So to do that, I need to multiply row 1 by negative 4/3. When I do that, row 1 doesn't change. Row 3 doesn't change. And if I multiply row 1 by negative 4/3, I end up with negative 4, negative 20/3, and 8/3. So 4 plus negative 4 is 0. 1 plus negative 20/3 is negative 17/3, or 3/3 minus 20/3. And then 3/3 plus 8/3 is 11/3. The one downside of using LU factorization is we deal with fractions a lot more, which is kind of annoying. But it's always the same row operations. So here, my first one, I'm going to say R2 equals R2 plus negative 4/3 R1. That's my first one. My second row operation is going to be R3 equals R3 plus some multiple of row 1. I'm making this a 0. So I'm going to multiply row 1 by positive 4/3. So when I do that, I end up with row 1 doesn't change. Row 2 doesn't change. And if I multiply row 1 by 4/3, I end up with 4, 20/3, and negative 8/3. So negative 4 plus 4 is 0. Negative 4 plus 20/3, rather than do that in my head, I will look at my answers, is 8/3. And then 5 plus negative 8/3 is 7/3. And then my last row operation, I'm going to place row 3 by adding it to some multiple of row 2. I'm trying to make this a 0, which means I need to multiply row 2 by 8/17. When I do that, I end up with 3, 5, negative 2, 0, negative 17, 3, 11/3. And then if I multiply row 2 by 8/17, I'm going to end up with 0. I'm going to end up with negative 8/3 like I wanted. And then 88 over 17 times 3, whatever that is. You have your calculators. Use them. They're useful. So 8/3 minus 8/3 is 0. And then 7/3 plus 88/17 divided by 3 is 69/17. So that's what I end up with. So it's always the same 3 row operations every single time. Every single time. Row 2 plus some multiple of row 1. Row 3 plus some multiple of row 1. Row 3 plus some multiple of row 2. I'm going to erase this just for room. Clean it up a little. So it turns out when we do that, the matrix we end up with is just U. It's going to be our upper triangle matrix. Note, it is our upper triangle matrix. Essentially, it's what we would get if we were doing Gauss elimination, if we applied these 3 row operations. So it's the same process we do for Gauss elimination. However, for Gauss elimination, we also have our B vector. For LU factorization, we don't. But note, we have to always apply these same 3 row operations. Here they are listed out. The nice thing about LU factorization is that it's the same every single time. So regardless of what your A matrix is, regardless of what numbers are in there, it's going to be the same thing every single time. And it turns out, in order to find these factors here, all we need to do is take this number divided by this number, and then this number divided by this number, and then this number divided by this number, however it ends up. So it's the same 3 row operations every single time. Whatever we end up with ends up being our U, ends up being our upper triangle matrix where we have our lower triangle zeros. Okay, so we have our U. So we have part of our factorization. Now we need L. L is pretty easy to construct. L ends up being a matrix that looks like this. And then these remaining 3 locations are filled in using what's called our multipliers, using these numbers that we used in our row operations. So what we're going to do is this number was used to put a 0 here. So in that same location in L, I'm going to use that same number, but flip the sign. So this becomes a positive 4/3. This number was used to put a 0 here. So in that same location in L, I'm going to put 4/3 and flip the sign. So it becomes negative 4/3. And then this number was used to put a 0 here. So in the same location in L, I'm going to put that number and flip the sign. The reason why the sign is flipped has to do with what's called our elimination matrices. So it turns out that this elimination step can be performed by multiplying our matrix, our A matrix, by the corresponding elimination matrix. So if I did this same row operation on identity, I'll call it L21, it would look like this, where I would end up with a negative 4/3 in that 2-1 location. So the result here is I can do my row operation by hand like I did on paper, but from a matrix multiplication perspective, it's the same as if I took L21 times A in that order. So where L21 is my elimination matrix, or my elimination matrix, where I do the same row operation on identity. And it just so happens, I shouldn't say it just so happens, it turns out when I do that on identity, I end up with this additional term with that number, that multiplier, in the same location, in the 2-1 location. Same thing here. The corresponding elimination matrix looks like this. Where the product here is going to be L31 times L21 times A, where this gives me my first 0, and then if I multiply it again by this elimination matrix, it gives me my second 0. This is some background information. It's not really, like, you don't necessarily need to know about this in order to understand the process. But this is where L comes from. L comes from all of these elimination matrices. And it turns out it comes from the inverse of these elimination matrices, where L21 inverse is literally the same matrix with the sign changed on my multiplier, which is why when we put our multipliers inside of L, that's why we change the sign, because it's the inverse. That's essentially where I was going with this. Why we change the sign. Because it's the inverse that we're pulling together. Okay, there we go. So I have L, it's a lower triangle matrix. Notice my upper triangle of zeros. And then I have U, which is an upper triangle matrix with my lower triangle of zeros. So if I take L times U if I do this multiplication, I end up with A. Row 1, column 1 gives me a 3. Row 1, column 2 gives me a 5. Row 1, column 3 gives me a negative 2. Row 2, column 1 gives me 4/3 times 3, or 4. Row 2 times column 2 gives me 20/3 minus 17/3, or 1. And then I would keep going and fill in my remaining ones. If you do that multiplication, you end up back at A. So what we did through this process, applying those 3 row operations, 3 same ones every single time, those 3 row operations, we end up with a factorization of A. where we've broken up A as a product of a lower triangle matrix times an upper triangle matrix. Okay, that is the first way that we can find L and U. The second way, the second method we can use to find L and U is this method here. It's just an alternative method. It's not as crafty. Yes, 69 over 17. So the second way we can find L and U, which it's fine. It's a method. It's not my favorite. It feels like cheating. But essentially it looks like this, where we know that L is going to end up like this. It has ones along the diagonal, it has zeros in my upper triangle, and then I have my multipliers that show up here. So if I do it in variable form, it essentially looks like this. And I know that U is going to look like this, where I end up with a triangle matrix with my lower triangle of zeros. If we do this multiplication in variable form, if we leave it as these unbeknownst numbers, if we leave it in letter form, and I do this multiplication, row 1, column 1, I end up with U1. Row 1, column 2, I end up with U12. Row 1, column 3, I end up with U13. Moving on, row 2, column 1, I end up with L21 times U11. Row 2, column 2, I end up with L21 U12 plus U22. And then same thing over here. L21 U13 plus U233. So essentially, if I do the multiplication beforehand, I know this should equal A, which should be this matrix. 3, -5, 2. There we go. So Flora, that's a good question. On your exam, something like this, I try to advocate for not telling you a specific method to use. Use which one makes sense. One method, depending on what the question looks like, it might be easier to do it with this method versus another method. We might give you a hint on which one to use, but we probably won't tell you to use a specific one. So be comfortable. I mean, you can be comfortable with either. Try it with both. This one might be a little bit more straightforward if you aren't as comfortable with row operations. Yeah, it really just depends. Good question. And then we just do equal matrices. So if I set this side equal to this side, that tells me that U11 equals 3. This tells me that U12 equals -5. This tells me that U13 equals 2. And to be honest, your first row of U always looks like the first row of A. It always is the first row of A. So the first row of U always is the first row of A for LU factorization. Okay, so I have those three numbers. Woohoo! Move on to my second row. This one, L21 times U11 equals 5. I already know what U11 equals, so L21 times 3 equals 5, which means L21 equals 5/3. If you aren't as comfortable with fractions, this method might be more comfortable to use. Then my next one, L21 U12 plus U22 equals 4. I know what U12 is. I know what L21 is. I know what U12 is. Plug those in. 5/3 times -5 plus U22 equals 4. U22 ends up being 37/3. Keep going. L21 U13 plus U23 equals 3. Plug in all your known numbers. 5/3 times 2 plus U23 equals 3. And it turns out every single equation we have, there's only one unknown to solve for. And U23 ends up being -1/3. Nope. Yes. Yes. -1/3. And then for your last row, same process. It just so happens there's more variables to fill in. U31 times U11 equals 2. L31 times 3 equals 2, or L31 equals 2/3. L31 U12 plus L32 U22 equals 5. 2/3 times -5 plus L32 is my unknown times 37/3 equals 5. And this tells me that L32 ends up being 25/37. Notice the fractions we have aren't terribly nice. They're not the worst, but it's just more to keep track of. And my last one, L31 times U13 plus L32 U23 plus U33 equals 3. On your exam, feel free to plug in your numbers right away. I'm just showing you all the fun steps. 2/3 times 2 plus 25/37 times -1/3 plus U33 equals 3. And it ends up that U33 equals 70/37. Once we have all of our unknowns, we can just plug them in to what we know L and U should look like. So doing that, we end up with L that looks like this. Five thirds, 2/3, and 25/37. And then U ends up like this. 3, -5, 2, 0, 37/3, -1/3, 0, 0, 70/37. There we go. LU. Woohoo! We did it. So there's two methods to use. I prefer the row operation method. I really like it. I think it's fascinatingly brilliant in terms of its algorithmic nature and the fact that you have everything, the same steps every single time. I really enjoy it. It feeds to my logical side. But use whichever method you use. Some methods might be easier than other methods depending on how messy your fractions end up being. So, I don't know, try it with both. Okay, so why do we even care? I am not a mathematician. I'm sure that L and U have some wonderful properties that tell us more about the system of equations. The fact that we have a lower triangle matrix and upper triangle matrix. Next week, we will get into eigenvalues and eigenvectors, and there's something called diagonalization, where we can essentially decouple the system and get some nice properties out of that. I'm sure L and U have the same nature. I don't know. I'm not a mathematician. I just know we can find L and we can find U. So what we're going to do, as you may have guessed, we are going to use L and U to solve a system of equations. And you kids rise up. Yep. We're not going to get as involved, but yes. So let's say we have this system of equations. AX equals B. This is the same A matrix we just found L and U for, so it matches this exact one. So we've already broken up A into L times U. So if I rewrite this system, stop moving. I can rewrite it as L. Why are you moving? Times U. And now I have X. And I have B. Notice L and U are triangle matrices. If we remember from Gauss elimination, the goal is to get our matrix into a triangle form so that it's easy to solve, where we end up with one equation with one unknown, one equation with two unknowns, one equation with three unknowns. So we can easily solve for our system using back substitution. The same idea holds true for LU factorization. So essentially, what we do in order to solve this system of equations using LU factorization is first we break up A into LU. Then we can rewrite it as LUX equals B. Once we have that, I'm going to break it up into two different systems. Essentially, I am going to take U and X Come on. I'm going to take U and X. I can do this. Forget it. Forget it. I'm going to take U and X. And I'm just going to pull it down. And I'm going to replace it by another variable. I'm going to replace it by a variable called Y. Y1, Y2, Y3. So this is my Y. Such that U times X equals Y. So I have AX equals B. I factorize A, so it's LUX equals B. And then I break it up into two different pieces. I'm going to say UX equals Y. I'm going to replace UX by a variable such that LY equals B, where Y equals this. What this does is it gives me two different systems with triangle matrices. So using LYB, I can easily solve for Y. This one tells me that Y1 equals 7. This one tells me that 5/3 Y1 plus Y2 equals negative 12. Or Y2 ends up being negative 71/3. Once again, those beautiful fractions. And this one tells me that 2/3 Y1 plus 25/37 Y2 plus Y3. How about we write neater? Equals negative 17. Or that Y3 equals negative 210 over 37. Here are my Y values. So I can easily solve for my Y values. And in fact, it's really nice to solve for your Y values. They tend to be more straightforward. So that means when I have UX equals Y, I know what Y is. So I can just plug it in. 7, negative 71 thirds, negative 210, 37. And now with UX equals Y, I can easily solve for X. So this equation here tells me that 70, 37, X3 equals negative 210, 37. Or that X3 equals negative 3. This one tells me that 37/3 X2 minus 1/3 X3 equals negative 71/3. If I plug in my negative 3 for X, it tells me that X2 equals negative 2. And then this first equation, such nice whole numbers, tells me that 3x1 plus negative 5x2 plus 2x3 equals 7. If I plug in x3 and x2, I find that x1 equals 1. And there we go. I have my solution. You always have to do Ly equals B. Otherwise, Ux equals Y. Otherwise, this is unknown and this is unknown. So you have to solve for Y first. You have to solve for Y first so that when you have Ux equals Y, you know what Y is. So there was some confusion on the quiz and some people had to try it a bunch of times. So given a system of equations, if we are going to solve for X using LU factorization, the first thing we do, put it in the form of AX equals B. And in fact, that's the first thing you do for like any system. Whenever you're using one of these linear algebra methods, we always want it in the form of ax equals b. Sometimes you'll be given it in the form of ax equals b. Sometimes you'll be given your original system of equations with the 3x1 plus 7x2 plus whatever. But we always need it in matrix form. We need A, we need B, X is our vector of unknowns. Sometimes that looks like it's the augmented matrix, sometimes it's not, but we need those pieces. We need A, we need B. The second thing we're going to do is we are going to factorize A. So when you say A equals LU, we can use that alternative method where we know what L looks like, we know what U looks like, and we multiply those two matrices together in their variable form. Variable, that's the word I was looking for earlier. But we can also use our row operations. So row 2 equals row 2 plus some multiple of row 1. Row 3 equals row 3 plus some multiple of row 1. Row 3 equals row 3 plus some multiple of row 2. Apply our row operations on A. Once we do that, so technically it's 2, 3, 4. Our next step is to rewrite our system as LUX equals B. Plug in L and U for A. Then we're going to write our two separate systems. UX equals Y, LY equals B. Once we do that, solve for Y. Not a Y. Solve for Y using this one. Once we have Y, solve for X. We're missing something. There were 9 steps in the quiz. I can't remember everything. I did it this morning, so I know there's 9 steps. I just can't remember which one I broke apart. But anyway, these are our steps. Set it up as AX equals B. Find our LU factorization of A. Apply those 3 row operations. Put together your L matrix. Thank you very much. So after we do our row operations, this gives us U. Then we need to put together L matrix using these numbers. Thank you. Thank you. There we go. Now we have 9 steps. So your row operations gives you U. Use your multipliers here to fill in L. Remember, you need to change the sign. Then we can write our system as LUX equals B. Break it up into 2 pieces. Solve for Y, solve for X. Bam, we're done. So there's a lot of steps here, but it's the same steps every time. I mean, I wrote a MATLAB script that essentially shows my work for me because it's the same steps every single time. You cannot deviate. You do not deviate from these steps at all. And when we do solve for Y and we solve for X, it's pretty straightforward because we have our triangle matrices. So we write our equation with the least number of unknowns. Then we use that to solve for our next unknown, and then we use those 2 to solve for our last unknown. And there we go. This is for a 3x3. It's the same process for anything bigger. It's just depending on the number of row operations we have. So for a 3x3, we have 3 row operations. For a 4x4, we would have 6 row operations. So if we look at a 4x4, let's say this is our 4x4. The same process holds true. L is still going to end up looking like this. Oops, 4, 3. U is still going to end up looking like this. So we can do our multiplication with those L and U and use that method. Solve for equal matrices. We can do that. That's completely fine. There's obviously more involved here. Or we can do our row operations, which our row operations are going to be the same every time. First, I have row 2 equals row 2 plus some multiple of row 1. Then row 3 equals row 3 plus some multiple of row 1. Then row 4 equals row 4 plus some multiple of row 1. Those are my first 3 row operations. Essentially, I'm finding zeros in my first column, always using row 1. So for this matrix, in order to get a 0 here, I multiply row 1 by 1. In order to get a matrix here, or in order to get a 0 here, I multiply row 2 by -2. And then to get a 0 here, I multiply row 1 by 1. So there's my first set of multipliers that go inside of L. I do my 3 row operations to put a 0 here, here, and here, always using row 1. And if you remember, this is the same process I told you that you can use for Gauss elimination. So that means in L, this ends up being -1. In the 2, 1 location, ends up being -1. It comes from this number with the sign changed. This ends up becoming 2, this number with the sign change, and this becomes -1, which is this number with the sign changed. So after I do those 3 row operations, I end up with, I'm not going to show all the work for all of them, just for time's sake, but I end up with -1, -3, 2, -3. Row 2 ends up being 0, -5, 3, -3. Row 3 becomes 0, 3, -5, 5. And then row 4 becomes 0, -6, 5, -1. My second set of row operations, I'm going to say row 3 equals row 3 plus some multiple of row 2. And row 4 equals row 4 plus some multiple of row 2. So I'm finding these numbers using row 2 to do it. So for this matrix, to put a 0 here, I need to multiply row 2 by 3/5. And to put a 0 here, I need to multiply row 2 by -6/5. And I easily found those numbers because I took this number divided by this number, 3/5. I manipulated the sign in order to make sure it was the opposite, but 3/5. Then this number divided by this number. Once again, manipulating the sign in order to come up with my number. So it's the same process every single time, which means that L32 ends up being -3/5, and L42 ends up being +6/5. Once I do those row operations, I end up with row 1 doesn't change. Row 2 didn't change. Row 3 ended up being 0, 0, -16/5, +16/5, and then 0, 0, 7/5, 13/5. And then my last set of row operations is just to find my remaining L value, where I take R4 equals R4 plus some multiple of row 3. So in this instance, I have 7/5 and -16/5. In order to figure out what this multiplier is going to be, I'm going to take 7/5 divided by 16/5, or 7/16. Which means this ends up being -7/16. There we go. L is put together. Woohoo! When I do this row operation, I end up with 0, 0, 0, 4. Nice whole number there. Sneak attack. So I've got L put together with all of my multipliers. I constructed L as we went along. And U ends up being this result here. U ends up being my result. No cupcake panda because I want +2, -2. I have a -2 here. So I want them to be opposite and equal. So if you're ever confused on what your multiplier should be, essentially think about it as an equation where if I take, so I want this number here to be a 0, and I need to take -2 plus some multiple of row 1. In this instance, a -2 or a -1. So L in this instance should be a -2. So that's a really good question, just because it's, so on your final exam, you might have a variable in here. Like rather than it being -2, you might be given A. And you might be told what L31 should be. So this is where you might have to do some of that rearranging and thinking, where you know you want a 0, and you're saying, okay, so I want A plus, let's say L3 is supposed to be 5, plus 5 times row 1. And then you might have to sit there and work out what would A be given this scenario, given this situation, if L31 equals 5. So it's important that we understand essentially where all of our numbers are coming from. And the sign thing is, it is. You want them, in this instance, explicitly, you want them to have opposite signs. So I want this to, if this is a -2, I want this to have a +2. Yep, okay. So once we have L put together, once we have U, if we were given, so yes, AP, that is a really good point. But keep in mind, we need to be explicit on how we're defining our row operations in order to fill L. So if you subtracted it, you're not adding that number anymore, you're subtracting it. So when you flip the sign, you need to make sure to take into account that you're doing the subtraction versus doing the addition. So yes, you can definitely do that subtraction, but we have less freedom with these row operations because we need to know exactly how we're going to fill L and what that sign is going to be on L. So you need to be careful about the row operations or that multiplier, what you're doing, and that's why I'm strictly defining row operation 3 as, where is it? As this, where I'm adding some multiple of row Y. You can define it as row X minus some multiple of row Y. That's completely fine, but just keep in mind that negative sign and how you're going to account for it and where it shows up and where you flip it and all that fun stuff. Yes. Okay, those pesky signs in linear algebra, they're everywhere and they're annoying and they always mess you up. Okay, there we go. We have a 4x4. If we had a system of equations, if we had it in the form of AX equals B, our process would still be the same. We would still set up A as LUX equals B. We would still separate this out as UX equals Y and LY equals B. We would still solve for Y first, and then we would still go back and solve for X. But note, for our LU factorization, using our row operations, we are strictly using row operation 3, where U is our result once all the row operations are done, and L is filled with all of our multipliers from those row operations. Okay, that's all I have for today. I took the whole time this morning. But if nobody has any questions, we can be done. So, yeah. Hopefully all that made sense. Any final questions? So U is the result after we do all the row operations. So essentially, U is your REF. Just keep in mind, though, that we're just doing this on A. We are not doing this on the augmented matrix. U ends up being whatever our lower or whatever our upper triangle matrix is, with all our zeros in the lower left triangle. So for our first one, we applied 3 row operations. This one, and this one. This was our result. After those 3 row operations, that's going to be U. For this one, we solved for U using that method, so it didn't really follow. For this one, we applied these 3 row operations, then these 2, and then this one. Whatever we ended up with here after our final set of row operations, once we get our lower triangle of zeros, that is U. It's not really a different method. It's like the same method, but like stricter. Oh, does the homework ask you to write out your elimination matrices? Your elimination matrices are these ones here, where it's identity matrix, your identity matrix, where the multiplier that shows up in your row operation shows up in the same location in your identity. So Sophia, yes, you find U, but you have to use those row operations. You can't use any row operations you want, like you did using Gauss elimination. You have to do just those row operations. Can you keep negative 4/3? Yes. So in your elimination matrix, you do not change the sign. The inverse of our elimination matrix, you do change the sign, which is why it shows up in L, your final L with a sign change, because L is composed of L3-2 inverse, L3-1 inverse, and L3-2-1 inverse. So L is composed of the inverses of our elimination matrices. However, when we write the direct elimination matrix, that's not the inverse, we keep the sign. So there's lots of moving pieces. Your elimination matrices, like I said, it's not essential that you know about the elimination matrices in order to do the LU factorization. Because, I mean, we wrote out the 4x4 factorization without writing out any elimination matrices. But this is essentially a very algorithmic matrix multiplication method, where we are effectively multiplying our A matrix by all of these elimination matrices. Yes, so the elimination matrix is identity with just that one number changed. So for L2-1, it's in the 2-1 location. For L3-1, it's in the 3-1 location. For L3-2, it would look like this, where in the 3-2 location, we have our negative 8/17, or positive 8/17. The multiplier that shows up in our row operation. What do you mean by that, Flora? We can't add the numbers in the same matrix? Context? Yes, you will always have a new identity matrix. So L2-1, L3-1, and L3-2 are 3 separate matrices. L is composed of all 3 of them, the inverses of all 3 of them, but they are individual matrices. Got it, yeah. You're not adding the 4/3 to L2-1 because L2-1 only is for this location. Only for that one single row operation. Okay. Good questions. Any final questions? Yes. Yep. It's always identity with the multiplier in the same location that we got the 0. Keep the sign. You flip the sign if you're putting L together. You keep the sign if you're putting the elimination matrix together. Okay, a question on homework 11. I will answer this and then we'll be done. 11, problem 2. So if you think, so there's a property of determinants of how to find the determinant from a triangle matrix. To find the determinant of a triangle matrix, where either the upper triangle or lower triangle is full of zeros, then it's really easy. You just multiply the elements along the diagonal. It's really straightforward. If we don't have a triangle matrix, then we need to use cofactor expansion, which for a 4x4 and a 5x5 is complicated, especially if there aren't that many zeros. So the benefit of solving for row echelon form is so that we can have that triangle of zeros. Yeah. Okay. With that, I will see all of you guys on Wednesday. On Wednesday, we will go through essentially LU factorization, but we're going to add in one extra twist. And then we'll be done for the week. One more week of material. Okay. I'll see you guys all on Wednesday.